So yesterday, I said I had a few small things to talk about, which I can do, and I don't know how long it'll take. But we can go into that. So, we're all thinking, well, some of us are thinking about hierarchical sort of actions and goal-oriented behaviors. And so I've been thinking myself, personally, I've been thinking about little pieces around that, like, how would they, the thing that's really puzzling to me is how do we take some sort of action I know how to do, or I might come up with, and I can implement it using different parts of my body. I might do it by using my right hand or my left hand, or I might implement the same behavior using my eyes with an eye tracker, or trying to get, Jose to do it by talking to her. So there's all these different ways that, we are able to achieve a goal, even though the goal is the same. Somehow we're able to decompose this in the hierarchy and figure out which parts to do, how we can come about it, and we can overcome it. But if I'm trying to do something, I'm trying to open the door and my right hand is occupied, then I might, transfer what I'm carrying, or I might use my left hand. So it's just puzzling how this all happens. And the good news is I think we're starting to have a real understanding about hierarchy, at least in terms of compositional objects. And as I said, I think that's the key insights there are going to apply here as well. So I have one small topic related to this. It's sort of related. It may not be exactly obvious how it's related, but I'll just present it. And I thought it was kind of for me, it was a nice little insight, or at least a clarity. Am I not sure? I'm probably not sharing my screen. I have to share my screen.
Yeah, no, don't worry.
Here we go, share my screen. And there we go. All right, so in theory, you should be seeing my PowerPoint presentation here, right?
Yep.
Right. All right.
Well, I guess I'm not helpful because I can see.
So this again, don't get your hopes up. This is a pretty simple little thing I put together here. So one of the things that that is conventional neuroscience dogma is, if you look at two regions in the cortex, I just label them 1 and 2. That could be V1, V2, S1, S2, whatever. Two hierarchical regions is that you start out, the first one, you have like small receptive fields, meaning that the cells in that region don't. By the way, I'm showing 5 columns here, even though they're separated. That doesn't mean anything. It's just showing you some columns. That you have these small receptive fields, meaning the cells respond to a small part of the retina, a small part of the skin, or something like that, a small part of the cochlea. And you have these simple features. This goes back to Hubel and Wiesel, like, oh, look at these edges and so on. And then you go up the next level, and you find cells that respond to a larger area of the sensory organ, and the features that they detect are complex. Very quickly, it becomes very difficult to actually characterize these features. I mean, in the beginning, they say, oh, these are edges down here in R1, but then when you get up to here, like, well, there are all kinds of weird stuff, and they try to spend a lot of time trying to figure out what they are. And the basic idea that was proposed a long time ago, well, the obvious way they thought this would occur is that somehow these lower columns, which are each detecting some small feature, are converging onto cells in the upper column. Therefore, they're representing a larger area of the retina, a larger area of the skin, and they combine a bunch of simple features into more complex features. That is still, I believe, the standard dogma in neuroscience. But it never really worked for me. I had always these questions about it because it looks really simple here. But in reality, if you draw in all the arrows, well, there's every column in R1 is projecting to lots of columns in R2, and every column in R2 is projecting back to lots of columns in R1. It's actually not even clear if it's diverging or converging. It's just a lot of it just never made a lot of sense to me. And every time I tried to figure out how information would flow from a column to other columns, I always had difficulty with it. I know this. I think this is similar to what's going on in deep learning networks, and it works there, but it's not what's going. I don't think it's what's going on in the brain. So I could never get this to work in a way like, oh, how to build this. So the thousand brain theory, our recent work on compositional objects, shows a very different interpretation. In fact, you can get the same properties with just 2 columns, one hierarchically above the other. And now the theory here is that, well, the complex features in R2 are caused because in R1, there's spatial temporal integration. So you can look at those simple features in R1, they detect those, but they don't detect the output of R1, which is typically a more sparse distributed representation, and it's not easily characterized. But because R1 is combining inputs over multiple points in space and multiple points in time, R1 creates a more complex feature, which we would call our object output of the column. The increasing size of the receptive fields in R2, there's two possible reasons for that. One, obviously, R1 has already done most of the work. R1 has already said, okay, I've already integrated a bunch of stuff over spatial area. I'm passing the result of that. But I think, but there's probably something else going on as well. I wrote the first one here, increasing RF in size in R2 is caused by spatial temporal integration in R1. And then I said, and or changing scale. So I've always had this belief, and it's just a belief, I have no proof of it whatsoever, but there's some evidence that the scale of R2 in terms of its reference frame is larger than R1. And we see this in the entorhinal cortex where you have adjacent grid cell modules that get larger and larger, meaning, what does it mean to get larger and larger? What it really means is the rate of change in the grid cells relative to the movement vector changes. So if you're moving at some constant velocity and the grid cells change slower, that would be a larger scale, right? The space, you have less resolution in your space, but you have a bigger space. I think that's going on here, and I'm not sure if it's required, but I think it's going on. So I think my first assumption is, okay, R2 is naturally going to be modeling larger spaces just because of the way the system is set up. It's not learned that, just like the entorhinal cortex. And but also, you know, you got R1 is already passing things which are larger to R2. Now, the important thing here in our theory was that the reason this works is because R2 and R1 are co-located. They're looking at the same physical space in the world. So they're both modeling the same point in space. One is modeling a parent object, one is modeling a child object, and we can assign the child object to the parent object on a location by location basis. So as the sensor organ moves, both of these columns are moving with the sensor organ. Interesting, R2 would be changing slower than R1, right? R1 location might change, and R2's location might change less or not change at all. But I think that all works. But the point is, the key to the whole discovery of getting all the coffee cup variations working was that these two guys are looking at the same point in space, and therefore we can assign at any point on the cup what the same point on the logo, something like that. And that was the key. So we can achieve all these, this larger RFs and complex features and smaller RFs and simple features just with two columns. We actually don't need more than that. We don't need any convergence or divergence. I actually don't, we'll come back to the actual connections here in a second. Of course, we don't just have two columns. We have multiple columns. And so we have this concept of voting where these columns in the two different regions are coming to a consensus. But I don't think that changes anything, really. It just means that they get each of these columns in R2 and each of these columns on R1 are going to reach a consensus about what they're seeing, but still the learning occurs on a column by column basis. It just the horizontal voting is just to make sure that we get to R1 and R2 know what object they're looking at more quickly. But all along here, we see that the columns are still basically one-to-one voting on location to location. Now, this doesn't mean this is happening in every column in V1 or V2. It just means in the fovea area at some point where these columns are looking at the same object, it would be occurring. So that's basically our theory about how this is occurring, as opposed to the thing on the left, which is the conventional theory. And of course, the one on the right solves a huge number of problems which no one ever even tried to attempt on the left side. So we have great confidence that that's correct. I thought this to me was a really great insight. It just means when we're talking about any kind of compositional structure, whether we're doing down the hierarchy, especially if we're going down the hierarchy to the motor behavior, we should be thinking it along these lines. Now it's more complex than this. In a second here, I'll show you. So this is a figure from the paper where you're supposedly going to finish sometime. And this is showing the three columns in three different regions, R1, R2, and R3. And the feedback connections we were just talking about are these purple ones, just to review, where layer 6A, we believe that's the location in the space in this column and in all these columns. And so the location in R3 is projects first to the location in R2. And we know that this is a very narrow projection. So by narrow, I interpret that mean that R3 and R2 are looking at the same point in space. And so we're basically associating the location in, if you will, the coffee cup with the location on the logo here. And we're learning, and we have all this worked out in a fair amount of detail, but we're associating at this point in the cup, you should be at this point in the logo with an orientation and scale, things like that. So that's going down here. Of course, we do have these long range connections in layer 1, which don't fit what I just talked about. They go beyond this first column. So we have this very targeted projection in layer 6, 1-to-1. That's what I showed in the previous slide. That's this targeted connection here. And that's the forward one is this one. And yet we have obviously a broader spread up in layer 1 that goes beyond that. That's a little bit harder to interpret actually, but it seems to be important. Of course it's important. And so that's sort of like, well, what do we make of that? Clearly R3 is able to tell multiple columns in R2 something about what's going on. I've always often wondered if, like, how do all the columns learn at the same time? Like I want all the columns, there's some capacity to the whole system, so it can't learn everything. But these 3 columns can't be just learning specific points. They have to, everyone has to be able to take the role of any point in space because the object can move around. So I always thought that maybe this is sort of a learning signal. It's like saying, hey, you know what? I'm passing to you, to all the other guys. You could learn, if you're not getting any input, maybe I'll help you train or something like that. I don't really understand it. And it may play a very central role in how we do, how we are able to model and execute behaviors in different modalities and so on. Anyway, I'm just reminding us, talking to myself here in some sense. Okay, well, some of this we understand, some of it we don't understand. And believe it or not, that's the end of my little presentation today. I think this idea that we have in our theories is contrary to almost everyone thinks in neuroscience. And I think it's really it was helpful for me to remind myself when I think about not just compositional objects, but compositional behaviors that I have to think in this paradigm. And I have to, somehow we have to work with these connections. There are no other connections besides this that we know of. Well, there are some. I mean, yes, there are. There's long range connections from other places, but these are the primary ones. And so it's like somehow we have to make this understand it. So that's really it. We can talk about this. Maybe everyone got this and knew it already. But just writing it down like this was helpful for me. And just making clear, like, yeah, because I was starting to think along these lines on the left here. I was starting to think along, how do I, spread from this column out to here? And I think, no, really, I got to look at it like this, and like this. These are the ways to think about it. Where it's tempting to think about it this way, and I don't think that's right.
Yeah. On this note, I guess one thing I was just thinking about randomly while we were talking about this was so yeah, I guess we know there's fan-in connections to higher level columns, and we've kind of accounted for this partially with the current setup where, like, sorry, on like the previous slide, that like
Do you want me to bring up a picture from the paper? I have the paper here.
I don't know if we actually had but maybe I can just I think I can just draw on this. Sorry, 2 seconds.
You want me to stop sharing, or you want to do this up?
No, this is great actually, because then I can write on this.
Okay, well, I shouldn't have interrupted you. Keep going.
Oh, you're gonna use your iPad?
Oh,
Yeah.
I didn't bring my
I can
iPad.
also share a figure that we drew like 1.5 years ago or something.
Yeah, I think you drew one, Vivian.
If you want.
Oh no, okay, I think this is.
You drawn off to the side there. A little green.
Can you
line.
see?
Yeah.
Oh, okay, so it does come, but it's slow.
yeah, it's a little bit,
Okay,
there's one
I need to be
to consider.
patient. Okay. I mean, I don't know if this really helps, but I'm just thinking, why is it so slow? Yeah, we know there's fan-in connections, and right now, yeah, we're generally still kind of assuming that there's some degree of co-location.
How do we know those fan connections? What are we talking about specifically there?
It's not just the receptive field, it's not just the physiological properties, it's actually the connectivity. I remember looking that up.
You know, it's funny. I was trying to remember whether that was. I mean, the details matter. Just like in my next slide, there's fan out, but they're not equivalent, right?
Yeah,
There's a specific fan, there's a specific connection 101, and then there's a fan out. And so I was looking. I was trying to recall. I didn't do a literature search, but I was trying to recall. Have I seen? You know, what do we know about those actual connections like that?
Right.
And all I can recall is that. I know that people assume that they look like this based on these properties.
Yeah, no, that's what I thought at first as well, but I'm pretty sure, I mean, I can maybe try and find it after this, but I'm pretty sure I eventually found the paper where they talk about the anatomy. But anyways, I guess just what I was going to get at is with like, yeah, this co-location assumption seems reasonable in a lot of cases, but I guess in some ways it might constrain us. But then it also just feels like if we apply the same transformation we are doing for voting, then that's not really an issue anymore. Like the same kind of transformation we're doing for voting could also could basically account for any difference in the pose of the sensor module for this one as this one.
Well, you know what's interesting about this, Niels, is that I think I can do the entire compositional model using 2 columns. And
yeah, so you potentially don't need it, but
right. So that tells me that the other stuff is, if it's there, it's not the requirement. It's somehow it's helpful. So like voting is one example. Another example I was trying to talk about is like helping these columns learn, right? Like, training columns that aren't actively involved in this to learn the model. So like we can train multiple columns that aren't even experiencing anything right now. So there could be there seems to be other reasons. It's not a fundamental requirement. If I can do the whole thing in 2 columns, then it puts it into this category like voting. It's like there's something else that's really valuable those connections, but it doesn't seem like they're required. But by the way, I don't know if we can do the object behavior with 2 columns. I'm pretty sure we can do the compositional structure modeling with 2 columns. And I'm going to try to work on trying to get it to work with 2 columns, because that would be the beautiful result, right? That would be the nice result.
Yeah, and I guess if nothing else, I mean, this was more an aside. I just thought it would be interesting to maybe quickly chat about that. I don't think this relates to the hierarchical policies, because yeah, ultimately those are going to depend a lot on the top-down connections, and we know what those look like. And like you were saying, those are going to L1, so those kind of by definition cannot give some sort of location specific. Except for the co-located reference frame.
Well, it wouldn't be meaningful for columns. The co-location wouldn't be meaningful if the columns were looking elsewhere, right?
Yeah.
So I don't really understand it. I mean, I think it will become clear shortly, but right at the moment I'm confused by it. One point I said, those projections to L1 could be just like, what is the object that you're supposed to be observing, but not the location? But if it's coming from layer 6A, it's the same cells. We believe those are specific locations. So I'm providing a specific location to L1 to a column that's not at that location. So like, okay, I don't know what that means. Here's an idea. Here's an idea. Remember, if R2, the space of R2 is larger than the space of R1. Imagine it was quantized. So one location in R2 would correspond to multiple locations in R1. And so imagine R1 is looking at 3 different parts of the logo, but those all fit within the one location in R2. Like R2 doesn't have the resolution to distinguish those 3. So basically, R2 is saying, at my location, here I am at my location, as best I can resolve it, right? It's like saying, this location.
Yeah, I mean that's kind of what we're doing at the moment. I think where it's kind of like, yeah, R2 has a lower frequency, or like, yeah, like a coarser model.
Yeah,
And
maybe
so,
I can share the figures that
yeah,
we
that might be helpful.
talked a while ago.
Stop
If
sharing.
maybe that would be helpful.
Sure, I probably forgot these things.
Also, can I ask a question that I've been holding for like 3 weeks?
For 3 weeks, sure.
Well, since the last time you presented the hierarchical or compositional objects, and I know, I mean, this is very going against by a lot of literature, but does it have to be true that R2 always have a larger receptive field?
No, I don't think it has to be.
Yeah, like as in like and the reason why I'm making that is statement is like maybe R1 has like a general like sense, has actually the largest receptive field, or but then as we go higher in R2, R3, when we're trying to do something like interesting, we need to kind of focus on, like I can be looking at this like laptop. I know that I'm still here, but actually it's like hard for me to like I can't pay attention to everything that's here.
Right. But the beauty of that is at the higher level, it can say there's a laptop, and the lower levels can be taking care of all the details, and you don't have to be conscious of it, right? I don't know. A couple other observations worth making here. One is typically the first two regions of any potential modality are about the same size.
Okay.
V1 and V2. In fact, V2 is slightly larger than V1, at least in some studies. And but they're about the same size. So we don't see this. First of all, we don't see any kind of convergence in space size, right? In theory, you logically you might say, well, they have the same number of columns, which is kind of interesting. I mean, I'm just separating out that's a sort of separate piece.
I mean, you do have convergence after V2, but
what's that?
I think you do have pretty significant convergence after
Right. It does
V2.
get smaller after. It does get a lot smaller after.
What gets smaller?
Like V4 would be
like
smaller
just the
than
number of neurons.
Oh, okay, just
the number, and presumably the number of columns. But maybe the walk away from that is, first of all, it's a tangent to your question, OJ, but it seems like this works no matter how many columns you have in a particular region. Like somehow we can have small columns on top of bigger columns, and we probably can have bigger columns up, small regions on top of bigger regions. We might be able to have V2, if V2 is larger than V1, we have a larger V1, slightly larger V2 over V1. So I'm just separating out that's a separate tangential to your question. It feels totally logical to me that the receptive field sizes get larger as you go up the hierarchy. That is the receptive field sizes of the inherent ones in the grid cells. We know that the actual cells themselves do that, but that could be that could be integration, right?
Right.
And I asked myself that question, the same question you're asking. Well, does it have to be larger? Does R2 grid cell space have to be larger than R1? Not clear to me. And then I asked myself a different question, which is like, well, how would I feed in an R1 from one modality to an R2 of a different modality?
Okay.
Because at some point we have to, we're constantly combining modalities in ways here. And I haven't answered that question yet, but I have some interesting thoughts about it. It's like, oh, I have a movement vector coming in R2, which represents movement of one sensor modality, and a movement vector representing a different an R1, a different sense. What would we learn? Like I'm basically, I don't know yet.
Okay.
But anyway, I don't know. Your question's a good one. My assumption is that the spaces get larger as you go up. It seems to make sense to me, but maybe you can make the argument why it doesn't make sense to you.
Yeah. Or I guess just to keep it in mind that when we build on top of this, that maybe this assumption, just to also think about it in the other way, where what would happen if the receptive field is getting not getting smaller, but I guess with the cup with the logo, like maybe R1 we can see the cup, but maybe the logo part of it, let's say, is the interesting part. So I don't know. Like I guess
First of all, anything that's really small would benefit from a smaller space. Right. So I've always felt like when I'm reading the smallest font I can possibly read, that is, if I had two regions of different resolution, only the one that has the higher resolution that represents a smaller area of space would work. And I've always assumed that would be the lowest one down. It makes sense to me. I mean, that fits what the cells look like. Right?
I see.
And it just. also, if you think about behavior flowing down the hierarchy, I have some overall behavior, which is like, maybe sign my name. But then at some point, I have to actually move my fingers the smallest little amount to get the little ding, 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 ding. And and I can do that with my hand, I can do it with another tool, I can do it with a pen, or with my, there's a lot of ways I can do that. But it feels like the large scale thing is at the top, and that the actual motions I have to make each letter or something like that
Yeah.
would be at the bottom. It just feels, it seems intuitive to me, which could be wrong, but it feels intuitive to me that we're gonna go from large scale to smaller scale as we go down. But that's just an intuition. I'm giving hand waving arguments for it.
Or maybe we can think about like the goal of like making coffee, because so the goal Neil's presented last week that comes
Yeah.
from some subcortical region. So it could also make sense that it goes kind of from near the subcortical to the cortex. Like, okay, someone in the subcortical is telling me, oh, like I want to get energized, and we make the decision to make coffee, and then eventually that the kind of the higher level kind of gets as information goes, a higher level figures out like, okay, like here's a plan.
Yeah, but I think the plan gets executed differently as you go down the hierarchy, right? As I said earlier, I'm trying to open the door and I got something in my right hand, so I might just use my left hand where I normally wouldn't do that. And the higher goal stays the same, open the door, but at any moment in time I have to adjust. So maybe my pen is a little bit longer, it's shorter in my hand, but as I'm writing, I have to adjust my movements based on that. It just feels naturally that you have sort of a high level goal that gets decomposed into lots of small pieces. Those pieces, as you go down, those small pieces are in some sense optional, like you could have done it different ways, but the high level goal stays the same. And also,
but the high level goal is coming from the subcortex.
well, maybe. I mean, we can just assume,
Yeah.
right? We can just assume that as somebody is assigned,
Right.
remember I talked about maybe like a desired behavioral state.
Yeah.
And that could be subcortex. It could be you talking to me, asking me to do something, which then isn't like I'm thirsty. It's like, oh, I want to do what Jose asked me to do. So we just, from our point of view, I think we could just for the starters here, just say, okay, we've assigned a goal to this thing.
Yeah.
It could be an outer loop of Monty. And now we want to decompose it into a series of actions, and that series of actions will vary almost every day, moment to moment, based on the circumstances.
Yeah.
So it feels like, that just feels the opposite of going compositional structure going up and decomposing going down. I'm gonna work on, you can think about it, but I'm not gonna spend too much time thinking about it.
Okay. That's fair enough.
Yeah. So what were you want to show something, guys?
Oh yeah, so I just took it down because we were talking.
Yeah.
This was what we drew up after some brainstorming by the Bay sessions, I think a year ago. Basically, and this is kind of how it's implemented right now. That the higher level learning module has a larger receptive field. It also gets direct sensory input, or it can get direct sensory input
Right.
from like a lower resolution larger receptive field. And then the columns or learning modules from the lower level that it gets input from are the ones that have receptive fields co-located within its larger receptive field. But it could be at different locations in there. Learning module 3 would not be able to distinguish these locations. But they can all kind of feed into it.
And the assumption here too is that the 3 lower learning modules are modeling the same object, but at different locations, right? If they were the logo, they would all be saying it's a logo, but they're at different locations on the logo.
Yeah,
So
and they might not all send input at the same time to learning module 3. They just have a connection.
Why wouldn't they?
Like if they get noise, or they're like one of them is not sure about what it's sensing at the moment.
Okay, maybe, but let's take the assumption that they're all modeling the logo. So in that case, the inputs to learning module 3, even though they're coming from 3 different learning modules, 1, 2, and 1, 0, 0, 1, and 2. That's all. I remember the odd orders there. They're all basically saying the same thing. They're all saying it's a logo, it's a logo, it's a logo. They're not saying anything about location. They're just saying it's a logo. So there's no those three inputs aren't really converging. You're not creating something new in learning module 3. They're all saying the same thing. And if any one of them dropped out, it would still work.
Yeah, exactly. And that's kind of the second picture that basically, I mean, it's like a rough drawing of like that they would detach the different locations on the dendrite, and the one closest to the soma would be the one from the one that's at the center co-located of its receptive field from learning module 1. So if that one is certain about what it's sensing, that can activate the cell. If otherwise, it might look at the actual sensory input, or it can get input from the ones that are a bit more on the side of its receptive field. And it works with either of them. This one is kind of the most confident one, if you want to think of it in these terms. But I guess to me, it kind of is like a mechanism to add a bit more robustness into the system. Versus...
Yeah, it's funny. I don't think you actually have to put them in order along the dendrite. You could, but it doesn't have to be, because obviously, as we look at different environments, the one that's most likely going to always be the correct one is 0. And the other ones sometimes will be the same object, sometimes it'll be something different. And so you'll just naturally form more synapses to learning module 0 than you would to 1 and 2, unless 1 and 2 are consistently the same object, and in which case, you know what I'm saying, the neuron will naturally form synapses to the things that are the most consistent, whether you arrange them on the dendrite or not. It just, if learning module 1 is sometimes the same as learning module 0 and sometimes not, maybe those synapses just won't form, or maybe there'll be fewer of them or something like that. You know what I'm saying?
Yeah.
The system is very dynamic. We have to, and so it's not clear that they have to be in an order along the dendrite. Otherwise, I would say the pictures, I just keep the picture the same.
Yeah, I guess to me it was more the general idea. I mean, in Monty we don't have dendrites anyways, but more the idea that like if it gets input from all of them, like this one is the most reliable one. Learning module 1 or 2 could be actually on a different object if it's like right on the border, or might be more noisy or something. And yeah.
So I don't know, in Monty, I don't know how you do that. Do you like have different weightings or something like that? Or?
Yeah, so there are different options how you could select which input to use, or how you want to weigh them. Yeah, so basically a learning module can get input from all of these sources, but it could weigh them differently. And I mean, it's basically up to the person who implements it, how you want to weigh it, or if you want to just pick the winner or something like that.
Yeah, right.
Yeah, so I was thinking about motion, object motion, and where and when that's computed. And, you know, one of the thoughts popped in my head is we've got these converging inputs from multiple LMs that are spatially distributed in one layer or one tier of the hierarchy. Could it be that even if a corresponding column in the second tier of the hierarchy has roughly the same receptive field area, it's using its conversion connections to compute object motion?
Well, that's a good hand-waving argument. I'm not sure how I would implement that. I guess maybe today, my proposition today is I'd like to solve this problem without using converging inputs from multiple columns.
I see.
And it's like we solve sensory motor input by ignoring the hierarchy and by ignoring voting. We said it has to happen in a column, and that led to success. And so now I'm arguing if we're going to think about hierarchy, I want to first start with the case where you have one column in each region, and then if I should be able to get that to work, and then all those other things then they'll become clearer later. That's my hope.
Yeah, I mean, it's kind of like this is the whole principle of Monty. Like it's the same as we don't feed the whole image to one learning module. We feed individual patches to each learning module. Then they can vote with each other. So it's exactly the same principle, just one level up the hierarchy.
Right. So it's a divide and conquer strategy, right? Solve this problem with now we're gonna for all these years I resisted going to 2 columns. And people kept saying, let's solve this problem with hierarchy. I said, no, guys, you got to figure out what a column does first. And now I'm saying, okay, we're gonna solve these problems with 2 columns. We're gonna solve all compositional behaviors with 2 columns, at least to get started. And then once we understand the 2 columns, we can add some more. Anyway, that's again, this is basically I'm just sharing my current brainstorming, my internal thoughts right now. This is nothing set in stone. I said, well, I can tell you what I'm thinking about. That's what I'm thinking about.
I think
Yeah, I
direction
guess-
just up and down makes sense based on at least neuromorphology. So like a lot of the neuromorphology across the layers, like L1 and 2 are the most fanned out, but if you look at the direction or the angle in which the dendrite or like the axons and dendrites are pointing in lower layers, they're closer to the vertical orientation than out, I think.
Right,
So-
well, that's, I think that was the key to that image I showed from our paper, where the synapses are made in layer 6A and then they get to layer 1 spread out. That was I hope that's true. But it was like, that was a key piece of evidence to explain all this to me. So, right, so my point is, Jose, it can fan in and fan out, but the key part is the one that's co-located. That solves all of the compositional structure problems. All the problems we were struggling with for years about how the logo can be curved and oriented and doing all these things, like solves all of them. So I was like, oh, that's beautiful, it really is great. I'm not denying there's fan in and fan out. I'm just saying, I think it's misleading. And we don't want to rely on it. If I can solve the problem of 2 columns, and then let's do that, then we can say, okay, how do we expand beyond that?
Yeah, so I guess going to that question of like 2 columns, and then this issue of how do you do it kind of essentially with arbitrary objects, like the whole point that you can recruit, as you're saying, kind of your elbow or whatever it needs to be.
That's gonna take more than 2 columns, right? Right.
Yeah,
So
but I guess. I was just gonna say. Sorry, go ahead.
Yeah, what I would do in that case, I would say, okay, we start with 2 columns, and then we go to 3, 2 in R1 and 1 in R2. It's okay. How do I take the behavior I'm trying to do in R2 and not just decompose it in time in R1, but also decompose it in space in the 2 R1 columns? Just like that, the whole problem of like how I might write my name with my elbow or my hand, or make the coffee cup, pour the coffee with different actions I could take. All that could be maybe expressed in just 2 columns in R1. Well, in fact, don't even think of them as R1. Just you have 2 columns at one level. They could even be 2 different modalities or 2 different parts of your body. And say, how do I execute the behavior that's learned in R2 in either R1 or in either R1 or R1A or R1B? So just like start moving in that direction, because that would, if I can understand that, if you can understand how we could take maybe a behavior that was learned in just one of those R1 columns and now have it played back in the other R1 column, that gets at the core of the the tasks we've been talking about, where you can execute various tasks using different methods.
Yeah, and I guess I was just thinking that like maybe this won't help, but one thing that seems like it would help is just if those goal states are in the kind of a appropriately abstract kind of representation, in the sense that like if, for example, the goal state that you're kind of passing down the hierarchy is like apply pressure at this location, like there are potentially lots of body parts that can kind of answer that call and achieve that. And I'm just trying to think like how we can do it with a body part. Like, well, we've never used previously for like a specific task, like pushing your computer mouse around, but we understand that we can do things with our elbow more generally. And so I don't know, just something like that.
Right. But let's say, okay, imagine the 2 R1 columns, R1 and R1A and R1B, represent 2 parts of your body. And normally I push the button with my right hand, the right column. And so, but now, for whatever reason today, I have to use the other one. It sort of suggests that, okay, this is where we might start getting into things like wear pathways, because I have to figure out how to move the sensor attached to R1B is in a different location and has to move to the location someplace else. So I think by decomposing the problem into these simple 2-column and then maybe 3 columns, it just feels like we could resolve all these issues. And that's what happened with compositional structure. We had to give up on doing with multiple columns and just settle on like how the 2 columns relate to each other, and that solved the problem. So anyway, it's a suggestion on how to think about the problem. And I'm agreeing with you, Niels. I think we can solve all those problems that, just adding one component at a time. Okay, go from 2 columns and 1 column in R1 to 2 columns in R1, that kind of thing. And it could be as simple as, right, the goal is to have to get the object in R2 in some state, the button is pressed. How do we get that to happen?
Yeah, and I'm just thinking maybe like in those instances, like we might not have like a learned association between, our left toe or our elbow or whatever, and doing that particular behavior. But as long as we have a learned association to some sufficiently abstract primitive, like applying pressure for that body part, then then maybe it's just a bit easier to generalize in that kind of zero-shot way.
It seems like also.
Wouldn't the goal state be, I want the computer mouse to be in location X instead of?
Yeah, so I guess I was thinking like a couple steps down. So like, yeah, that would be a higher level one. And then at some point, like, I don't know, the learning module that maybe knows about computer mice or whatever, or is modeling where the computer mice is on the desk is like, okay, for the mouse to move, there needs to be pressure at this point on it. And then it's going to recruit something to apply that pressure. But rather than saying like, left hand apply pressure or right hand apply pressure, like maybe it doesn't know anything about the body parts and the body parts don't know anything about mice. But so if the one that knows about mice in a desk just knows like, okay, there just needs to be pressure on here, and then the body parts just understand, okay, one of us needs to apply pressure.
There's often the key to success here is picking the right problem to think about. I mean, and that's why I love the mug with the coffee cup with the logo on it, because it really exposed a lot of problems in a very simple example. The one I've been thinking about just yesterday and the day before is typing. And it's really interesting because when I type, I don't think about the letters at all, right? You just don't think about the letters. In fact, I asked myself, do I even remember the layout of the keyboard? And I couldn't recall it all. Like when you first learn to type, you have to learn where all the letters are on the keyboard. And now when I'm typing, I'm like, can I just recite all the letters as I go? I can't do it, actually. I have to think really hard about it. But I can type any word instantaneously, right? And so, but it requires that my hands are in the same position, right? That's why we have these little detents on the F and the J, so your hands are in the right position. And once you're in that position, it's all low, to me, that's all low-level memory. It's like I'm now executing a low-level motor command, and even maybe S1 or whatever, M1 is doing this. But as soon as if I try to do it like moving my hands out or in, maybe I'm locating my hands on the G and the H, so they're not in the normal position. I can't type at all. I have to think really slowly, where's the letter? Or if I was typing with a tooth, I'm trying to type with a stick or something, I have to think really carefully. So my point is, I'm using this as my thinking example. The simplest version of this would be like I have a single finger. It's located, my hand is located somewhere relative to the keyboard, and the task of that finger is to move to execute, certain like sequences. Like I'm typing with one finger, but I could learn to do it really quickly with one finger, just like I can do it with 2 hands. And then say, okay, so imagine I have 2 lower columns. One represents my right finger, one represents my left finger. And I've learned to type with my right finger just by moving it from some, my palm is in some location, and I'm moving it to some 10 keys, and I can quickly I can do that really quickly, but I haven't learned to do it with my left hand, my left finger. And so then I'd have to attend, if I was gonna do it with my left finger, I'd have to attend very carefully with where's my left hand, where is it relative to the keys, that kind of stuff. I might have to use vision. I'm just suggesting this is the example I'm using right now where you could have two very simple actuators, your two fingertips. One could learn in R1, could learn very complex, sort of sequences because it practices over and over again, no thinking involved. But if I want to do it with the other one, I have to think about it and attend to it. So I'm just throwing this out as a potential sort of problem that exposes all the issues that we might have come across doing this compositional behavior. And so like the top R2 might say, oh, R2 tells R1, type this word, these letters, or just this word, and R1 plays it out. But if I have to go to the other R1 column, the one that hasn't practiced this, then it would be very slow and I have to attend to it. And so these are the things that we have to do with in solving goal-oriented behaviors. So I just threw that out.
Yeah, actually the keyboard example kind of makes me think of an interesting. So I guess as well as like using arbitrary parts, like another challenge we've talked about is like coordinating systems, like how do you coordinate your fingers and things like that. But yeah, the keyboard example was just making me think. Yeah, we were talking recently on Slack about how like if we can kind of do anything in a model-based way, even if it's going to be really slow and use a lot of computational resources, then we can eventually then kind of just like learn in a kind of subcortical model-free place how to do it in a more kind of finessed way with balance and unconsciously and stuff like that. But I was just thinking like we've struggled with thinking how we are going to just learn to even like pincer grip or something like that, or let alone like, yeah, typing on a keyboard with both hands. But I guess to a certain degree, those things do kind of always, yeah, when you're doing them in the model-based way, it's almost like one at a time. It's serial. Like when you're first learning to type the keyboard, you have to kind of type with one hand at a time. And even for a child, I think it's a fairly complex thing for them to learn the pincer grip. They're like, first they can move the thumb and then they can move the finger, and then very slowly maybe then a model-free policy takes over.
Right.
Yeah.
And
so I guess it's just, sorry, go ahead.
The example I just gave is simpler. It's like really just have two movable sensor pads representing the tips of your fingers, and there's no coordination between anything. It's like one, I think it might get to, like even the pincer grip, you're moving two things.
Yeah, and I guess what I'm trying to say is like, what I was kind of thinking about on Slack was that like anything needs to be done at least slowly. It needs to be possible to do it slowly in a model-based way, so that we can kind of learn to do it efficiently in a model-free way.
Right.
But it feels like coordination, kind of by definition, is always going to be taken over by like model-free. Like we can do it, you can really slowly like, okay, I'm going to move my thumb and I'm going to move my finger, then I'm going to move my thumb, and then okay, now I've got the object and I can pick it up. But what you're really going to want to do is learn to do that in a model-free way, and then it's like, okay, now I just need to execute the pincer grip.
You're using the word model-free again. I'm not sure.
Okay. So, or subcortical, if that helps. Just find and replace.
Why do I need to be subcortical? Why can't I just learn this rote behavior in R1? I think I can.
I guess you can do it slowly, but
no. Why?
Yeah,
no.
I feel like, yeah. I mean, we talked before that we want to have everything that happens in the neocortex will be like model-based policies, because why? Right. Otherwise, why would it be happening in the neocortex if it doesn't need a model to do it? But I kind of like the idea how Niels formulated it, that when you do something using the model, it's always going to be a bit slow, because you have to kind of go through the model and calculate your movements. But then when you want to do motor coordination, like, I don't know, dancing or moving your hands, grasping something, whatever, that's all some stuff that you can initially do kind of clunky using your models, and you can do it. You watch someone do the dance move and you do it right afterwards, but it isn't smooth and not very coordinated. And then once you practice it multiple times, it gets a lot more coordinated and then turns more into a model-free policy where you don't have to think
Well,
about
I'm gonna argue that. I don't think it's a model-free policy. It's first of all, I don't deny that some of these things are learned subcortically. I mean, the cerebellum is really important, and so the basal ganglia and all this stuff. But I think the whole thing can be done in the cortex. So again, I'm imagining R1.
It kind of has to be. If it's not done in the cortex, then it's going to take you like 1,000 years to learn to do it subcortically.
Right. So I think the cortex has to solve all these problems. And
I think the only thing I'm suggesting that the subcortex can do is just to help the coordination bit. Like we can coordinate it using model based like cortically, but it's just going to be really slow.
Maybe. Well, look, take my example of two fingers. One has learned to type and the other has not learned to type. And the one that's learned to type could be, it's still model based. It's still going on in the learning module in layer region 1. But it can be very fast. It's basically, it doesn't have to calculate trajectories. It's learned the trajectories. It's like saying, I can calculate how to go from point A to point B using my model, but if I do it over and over again from the same spot, I don't have to calculate. It's like a sequence. I just learn, it's like a melody. I just learn it, and now I don't have to think about it. I just know, I've done this many times. It's just a sequence I've learned, so I just go follow the sequence and it's done. So I think the evidence we have from humans and other animals is that when we practice something, whether it's dance or whether it's typing, whatever, that the representations for those behaviors move down in the cortex, and therefore it's faster. You don't have to transgress multiple regions. There's no communications involved. These are learned sequences. And so they're essentially were learned based on the model. They're still happening in the same learning module, but I don't have to do the calculation in the learning module. I just follow the sequence.
Is there any reason why we would still need them to be happening within the learning module instead of subcortically if we're not using the model anymore?
Well, I suppose there's no reason to, but I want to solve it first in the cortex. The cortex has to solve these problems. Take the cerebellum, right? It obviously helpful for any kind of coordinated movements like this. If your cerebellum is damaged, then your movements are sort of jerky. They're not smooth. We're relying on the cerebellum to really grease everything up and make it work better. But you can still do these things without the cerebellum. They're just not as coordinated. It's just like clunkier. So I think for me, I want to solve how the cortex does this first. That's our goal in mind. It's like cortical models. Then we can ask ourselves, okay, what kind of other stuff do we want to wrap around this that is engineered or works in a different way or helps, makes things move quicker or whatever. But I don't think we can. I think we have to solve the problem in the cortex itself. So
I think that's kind of the point that Niels was making to us, especially on Slack, that like we need to be able to solve all these problems in the cortex, but then once it's being practiced and getting really smooth and coordinated, that those might be optimized subcortically.
Okay, so I think
who did that?
Yeah, and thumbs up. And so actually, I was thinking a little bit about this in like a write-up that I did in Google Doc. So first, I agree that probably everything is model-based, definitely during learning and even when we're doing fast. I think the doing fast, so when we're learning, I'm thinking of it as like, okay, if let's say we're trying to pinch the finger, we need to think about, okay, move the thumb, move the index, move the thumb, move the index, and it takes a while. In the baby and also in computation wise, because we need to consider a lot of things about the model to decide on this action. So there's some function that chooses that action, and it's in the beginning, like it needs to take a lot into consideration. But as we get practice, I think that function computation can be faster, or even that function doesn't need to depend on any model, so it becomes like model free. It's just and then I think the fastness comes from the probability of choosing the next action becomes like close to 1. Like if I did move my thumb one way, then the probability of choosing the next action, now I don't need to think because I have that function has been optimized so that it's the next, we immediately know what the next action is. Does that like,
The words all made sense, but I got lost.
okay,
So that's just me.
I'll also probably try to like. write
Yeah,
it up.
well, I think maybe to paraphrase, maybe like, yeah, I think the idea that even in the model-based policy, or like, in the models, in the learning modules, there can be kind of probabilities associated with certain actions, and
Yes.
that those can be learned and refined. Yeah, I think that's interesting that, yeah, because, yeah, I think that makes a lot of sense that like, you want to make coffee, okay, there's 80% probability you're going to do it the usual way you do, 20% you reach for the instant coffee or whatever, and whether that's like by the strength of neural connections or some other thing. But yeah, I mean, I think that makes sense. And then as you're saying, like maybe when you have high confidence, then you don't need to deliberate as much, and so you can kind of navigate through that faster. Yeah, so I guess if I don't know if this is what you were kind of saying, but that might be a case of like where a model-based policy can also improve over time. Like there are things which still require conscious involvement. Like they're
Right.
sufficiently complicated that they don't become just model-free subcortical stuff, but they can still become faster through practice.
Yeah.
I think this all can happen in a cortical region.
Yeah. So I think the cortex is responsible for choosing the actions, and I think the cortex has to learn the actions, and the subcortex is just the executor. Like
I think we should just.
Yeah.
All right, I'm going to pursue this. I think we should totally ignore anything subcortex for now, and we have to solve this problem in the cortex itself. I can see how the cortex itself, by learning these, I'm thinking through it in my head right now, how they can learn to do these things very rapidly. You could call them model free because there's no thinking involved, like when I'm typing, but that's still cortex. And it just means that I've learned a particular, given if my hand is in the correct position on the keyboard, then the behaviors I have to execute are rote. They're not, they've been learned. The first time I did them, I had to think like, how do I move my finger from the J key to the Y key? But after I've done that enough times, I don't have to think about it anymore. And it's just like, so it's still, there's still a model in that column, but I'm not using the model to execute the behavior. I'm just using a sequence that I've practiced over and over again, but it's still in the column. And that's how I think, that's personally, I think how we have to attack this.
So that's essentially like a model-free policy in Cortex.
Well, you could call it was learned based on the model.
But
And
it becomes like a model
it
free
becomes
because
a
it
model
doesn't
free
depend
only
on
in
the
the
model.
sense that because it's so practiced, I'm starting the same position. Think about it, really, my hand has to be in the exact same position on the keyboard. So we have to, that's why we locate the index finger on the J and on the F. And once it's in that exact same position, then how do I move them to get to the correct keys? There's no ifs, ands, or buts about it. It's that there is a single direction you have to go a certain distance. I remember early on in my career, I worked on laptops, and they were changing the scale of keys from the original typewriters to the IBM Selectric to the laptops, because the laptop makers wanted to make the keyboard smaller. And so they went from like a 13mm spacing to a 12mm spacing, okay? And initially this caused havoc. People who had learned to type on typewriters couldn't type because that millimeter was like, it just threw off everything. And so we had this huge amount of pressure to go back to the 13mm spacing. By the way, I don't know what they are now. They're probably 10mm now. But back then it was a lot, every keyboard was the same spacing until the laptops came along and they started to get smaller. And then people started complaining about them. And so people said, you have to go back to 13mm, but people said that makes our computers too big. We don't want to do that. So that was an interesting thing, how that rote learning got off. Of course, after you've used a laptop for a while, you adjust. That was the right solution. My point was, it's very, very precise, right? And so you've learned these rote behaviors. And at that point, you're just assuming that everything's the same. And once my finger's in the right position, that all the other keys are in the right position, I don't have to think about it. But it still could be happening in the learning model. It's just not using using the model anymore. It's just practice behaviors. those are just
I think we're all
anecdotes.
agreeing on that this is gonna need to happen and that we're gonna need to be
Okay.
able to do everything model-based and then be able to kind of learn model-free sequences from that. I think the only question that Niels and I kind of raised was whether the model-free sequences are still in the neocortex or whether they are then learned subcortically. But mechanistically, I think we all agree that this will happen. It's
Well,
just
I
a
think-
maybe it doesn't really matter.
I think, I can't, it's automatically, it'll be learned in the cortex, as far as I'm concerned. You know,
Yeah.
all these layers of cells, this is another thing I was working on, I'll maybe represent another time, I was thinking about mini columns. But I think all these layers of cells work on the same principle as the temporal memory algorithm, which is, you know, we have this sparsification in context. But when you have a thing set up of mini columns like that, it'll automatically learn sequences if it's presented to them over and over again. The temporal memory algorithm will learn sequences if it sees them over and over again, and then therefore it doesn't have to calculate anything. So it's inherent in the way the neural mechanisms work. I believe that if you practice something enough, it will become, quote, model free, in the sense that it will just execute the sequence without having to calculate. So I don't think you need anything subcortical to do this. So you may want to think about subcortically transferring it there, but to me, I think it's a distraction. I would rather not. I mean, we can all agree that Cortex has to solve this, but then you say, well, it has to transfer later to make it faster. I disagree with that. I don't want to do that. I think that's we should solve absolutely everything in the cortex, and then you know, obviously some mechanics in the body, maybe, I don't know, but
yeah, I mean,
but
from the implementation, it's exactly the same. It's just whether we say, oh, this is what would be happening in the columns, or this is what would be happening in the cerebellum. So like, if I would implement this right now, this wouldn't influence how I implement it. But yeah, it's just a question of how we would map it to the brain, I guess.
I think it's still cortex. I think the point where like the thing that I think about is just because we're not thinking about where to move to type, it's not, that doesn't mean that it's subcortex. I think it's just that just because we don't recognize that we're thinking about it, I think it's still cortex. It's just that
if it
in
doesn't,
predictive coding, like because there's no change in the actions that we did before, we're not really recognizing it, but it's still cortex.
so you know, I wrote about this on intelligence. You know, there's a lot of things you
Are you talking about
do.
the book?
What's that?
Talking about the book on intelligence?
On intelligence.
Oh, your book. Okay, sorry.
My book.
Sorry.
I wrote about this thing on intelligence, where and it's not my idea. I mean, other people come up with this idea too. So that imagine the cortex is executing a lot of stuff. As long as you can get processed low down, like typing, it gets handled in the lower region. Only when something requires attention, or something, you know, there's an error or there's something that requires attention, then it goes right all the way to the top. If you're attending to something, it's going to the hippocampus, you're able to remember it. It's like everything gets taken over for that. But so much of what we do in the world is handled by these rote behaviors in the cortex itself. Even compositional behaviors are taken care of. And so you're not aware of it. You were talking about attention, what you're conscious of. It only gets conscious when the rote behaviors don't work anymore. And then it bops up to the top, and then you say, oh, I have to pay attention to this and think about it. So I think there's a lot of complex behaviors that are happening in the cortex, compositional behaviors, as long as they are, as long as they have been practiced enough, right? So even like typing on the keyboard, the first thing I have to do is get my hands onto the keyboard in the right position. Well, you know, I don't generally have to think about that, right? It just, you put your hands in it. You've learned these behaviors from feelings, and you just know where to put things. You put your palms down, and then you adjust your palms to the right position. Then you find the J and the H key, and then, you know, J and the F key. So there's a complex hierarchical behavior going on that I'm not thinking about at all. And it's involving multiple regions in the cortex, and just because I'm not thinking about it doesn't mean it's subcortical.
Yeah, I guess it just seems like we don't have a very good model of the keyboard actually anymore, because like you said, if I ask you now, where's the O key? And
it's
you
really
look
hard.
at the keyboard, you kind of
Right,
have to mentally type a word with an O in it, and then you know where
Right,
it is.
but when I first started learning to type, I actually took a typing class when I was in school, grade school. the first thing you have to do is memorize where all those letters are and the whole keyboard layout. But now that we've been typing for so many years, I've forgotten it, right? You know, I don't need that model anymore. It's amazing. I was trying to like, can I walk through all the keys on the keyboard? And I was struggling with it. We can do the QWERTY one, that's easy, and you can do the ASDF one, you see that a lot. But then the other places, like, what the hell, I can't remember. But I can type words, no problem. All right, well, we can, maybe we're in agreement, maybe we're not, I don't know. But that's how I'm gonna be working on it.
Yeah, I
I'm
think
gonna be
as
working-
Vivian says, it maybe doesn't matter too much. And who knows if our language will change going forward. But yeah, I guess the main thing is that we agree that, yeah, some sort of model-based deliberate conscious control is what comes first.
Or unconscious once you've learned it to row. Right?
Yeah, that's why I said comes first.
Right. So I'm gonna, you know, the goal I would think about was like, I got two fingers. One has been practicing typing from some location and it does it automatically. Then I want to do it with another finger, which is not that finger, a different column, and says, oh, I haven't learned how to do this. So I'll have to think about each one. And that is a nice problem, perhaps. Very simple, 2 columns in R1, 1 column in R2. It's a behavior we can all think about. So I'm gonna, now that we're talking about it today, it seems like that's my, I'm gonna try to see if that works as a good, that's the mug and logo equivalent for sensory motor, for goal learner behaviors.
It's an interesting sensory problem too, because you do the action, but you see the change somewhere else, like the letter appearing on your screen, and you have the tactile sensation, but then what the change actually affected is the visual input. So I mean, on that note, it's also an
Also,
interesting
the other
problem.
interesting question was, what if my hand is not in the right position, right? And so I definitely use vision for that, right? I have to see where the laptop is, or maybe I look at the keyboard or something like that. So even just getting your hand or your finger in the right sort of base position could require multiple modalities. I think that's what you're talking about.
Yeah.
Well, I think it's a rich problem in that it seems like the mug and the coffee cup, I mean, the mug and the logo it seems like a rich problem where very simple, a few columns can expose a lot of the issues.
Yeah.
that we have.
And I guess one thing that feels potentially encouraging is like, because we're doing it in a model-based kind of slow way, I feel like that just makes it easier that, yeah, if it's like an abstract goal state, like pressure at a location, like I guess my first concern with that was like, okay, well then how do you coordinate like pressure at multiple locations and stuff? But again, if we're not worrying about that right now, because that only comes through lots of practice, then it's like, it's not that hard to imagine, okay, first you send the goal state, okay, you know, something that, yeah, basically like apply pressure at this location. And then, as you said, like if the hand's in the wrong location, then maybe the eye can see that and then that sends some other goal state. But like, it does feel like we can kind of serially break it down. And like any task can just be like serially broken down.
Right, that's the goal, right? To come up with something where almost all tasks are sort of combinations of the elements we solve in the simple task. But that would be that's the hope.
So
Well,
then
I got my
kind of-
marching orders. I'm gonna go think about typing with one finger. 2 fingers.
So just to make it like a concrete hierarchical goal, just to state it explicitly, I guess. So the highest level goal would, for example, be type the word nomenta, and then it would be broken down into get hands in location X, Y, Z, type N, type U, and so on.
Well, I would start with the hand being in the correct position, and then have to figure out how do I move the finger to the correct key. That would be the first thing I would do. And then that's an interesting, and then because it would ask us how do you calculate that, and you could show that if you practice it enough, you can start doing it automatically. You don't have to calculate again. I would start with there, and then later I would say, oh, well, now I have a problem of how to get the hand in the right position. Cause I think that might be a where problem, you know, we might have to, it might be much more complex.
Yeah, I guess I was thinking it would be more like, yeah, you start with you want to type Numenta, so then the next goal state is typing the letter N. Whatever knows about like a key says, okay, I need pressure here. So maybe it's like there needs to be pressure at this location in body-centric coordinates. And that's quite like a widely sent goal state. That's like something that lots of things can answer. And then the learning module associated with like a hand is maybe like, okay, well, I know I can apply a pressure, but I'm all the way over here. So I need to be approximately here. And then it sends maybe like a sub goal to its finger, which is like, okay, you can actually apply the pressure. So,
Yeah. But I'm going even simpler than that. I'm trying to avoid the where pathway altogether. So I'm trying to do this all in the model of the modeling space of the object. So the object is the keyboard. And the first thing I would start with is I have a finger which is located within the model, the keyboard space. And now I just have to move it to different parts of the keyboard. I'm trying to, again, ultimately have to get the hand in the right position. But for starters, I would just say, how do I turn up, type, here's a command to type a word. I know what the sequence of the letters are. How do I pass it down one at a time to the thing that says, okay, here's how I just move in the object space. I don't have to move my hand in any other space. It says like it's already on the J key. Now, how do I get it to these other keys? And then I would start with that. And then later we could add in like, well, how do I get my hand in the right position? But even just solving the problem, like, okay, take the word, break it down into multiple letters, and how do I learn that sequence is a good enough challenge for starters.
I have a question about how a column decides that it's going to do the action. So if you have a hierarchical thing that you want to accomplish and it goes down to a column that your finger says, okay, I'm going to press the N key. Does it have to suppress all the other columns that could have taken that action? Say, you're not allowed to take this action because I'm doing it. Or is that somewhere in the, how do you think about that?
Well, I'm thinking about doing this all in like 2 columns and then 3 columns. So there isn't a need to suppress. You're either going to use the first, you're going to do it with two columns, or you just have one finger and there's nobody else who's going to do the action. And then you can say, well, how would I use a second column do it? And then that's, whether you have to suppress or not, or you're just directing someone else to do it is the interesting question. So the answer is we don't know the answer to that question, but I don't think it's the right first question to ask. I think the first question to ask is, how do I do this with just 2 columns first, where I'm just trying to decompose a problem into a component, and then can I learn to do that quickly as opposed to using the model? Just do it by rote. And then once I solve that with 2 columns, then we can go ask, okay, how do we have multiple actuators, and how do we choose which actuator, and how does that, which is your question, Will, you were saying, how do I do, you said, how do I suppress someone, but it more be like, you could also say, how do I tell someone to do this and not tell other people?
Right.
I have no idea yet how that occurs, but I think it'll become obvious over time.
I thought a little bit about, well, I can also try to say something about this, and also something about where pathway a little bit. So I think, so like, let's say we want to type the letter N on the keyboard, and basically another way to paraphrase Will's question is, how do I decide I want to use the index finger as opposed to middle finger, thumb, or whatever? And so when I'm first learning to type, so let's say I have 10 options, I can press with any of the 10 fingers. But through learning, or like, let's say I saw somebody else type with their index finger on their right, then I might have a little bit more bias, or like higher probability of choosing that action. Like I will press the letter N with my index finger, and then the next time you have a history of like, okay, I have done this action by doing this. I have achieved pressing N by using my index finger. So now you again have a probability, but because you have experience that was successful, you have a higher probability of using that again, or you can explore and do like another finger. But after a lot of experience, you probably have a lot of evidence or higher probability that, oh, like I will always use my index finger because that's all.
Yeah, if you've had success once, you'll probably do the same thing again and again.
Right.
Yeah, this is interesting that once you've learned to do something some way, you've been doing your whole life, and someone comes along and shows you a better way of doing it,
Yeah,
it's like, why didn't I ever think of that, you know, because, you know, like, I see
it was
this.
never an option.
Well, I see them cooking a lot, my kids come on, they teach me like, hey, Dad, you're doing this the slow way, you know, why don't you cut the onion this way? And I'm like, well, I always done it this way, it worked, but then they show me a better way of doing it, I'm like, oh, I should have done that way, how do you know, but you get in this road,
Yeah.
you get in this pattern, this is how I learned to do it, so you just do it that way over and over again. I think it's natural to do that, right? Why would you explore unless it didn't work?
Yeah, unless you're feeling exploratory for whatever reason, but I think this also answers like how can that be fast, because now probability of choosing the action is close to 1. About the aware pathway, like when we're talking about like the goal states, goal is about going from one state of the object to another, like.
Well, that was the proposal I
Yeah.
discussed last week, whether it's right or not, we'll see.
Yeah, but well, going off with that proposal, I think, let's say the goal is we're tired and we want to get energized. The object that works, so that's the state I want to change, going from tired to energized. And the object that it applies to is us. So I think actually we're modeling objects like outside of the agent itself, but I think maybe there's a lot of columns dedicating to modeling the agent itself.
Yeah, well, I think when we get to these sort of very high level tasks, like you're saying, making coffee, it's clear that you have to move your body to different places, or you have to pick things up,
Right.
and at least picking something up is definitely like a aware pathway. It's like relative to your body.
Yeah.
I'm trying to avoid that. The typing example I'm using, it doesn't require that.
Okay.
And not initially, right? It might require it if I have to get my hand on the keyboard.
Right.
But again, it's breaking down the problem into the simplest components and then expanding upon that. So the simplest one I would look for something that absolutely doesn't require a web pathway.
Okay.
You know, just trying to understand how do I manipulate an object. In case of the typing example, the goal state would be literally just be, I want this word, right? And it turns out there's a series of actions that have to be taken to get that word. Maybe the word's on the screen or just the word appears or someone speaks, I don't really care. The goal would be like, you know, get the computer that have that word on the screen, type of thing. And so the goal is implement this word, and that requires a series of actions on the of the actuator to do that. But those are all, once my finger is located on the J key, then there's no, as far as I can see, there's no aware pathway calculations. Just how do I manipulate the object with my hand, the object being the keyboard, to achieve a particular state. Anyway.
It's gonna be a difficult example to do with just 2 columns, just because of the multimodality property of it. Like, it's hard, it would be very difficult to type that word with only one touch sensor.
Why is that?
Like, I mean, for one, you can't distinguish the letters using touch, the keys using touch. And then you don't really know, like, what if the word actually appeared on the screen. I mean, you can kind of do the sequence.
Right. We would try to. Well, yeah, making this all up and sitting here making it up. I would try to avoid any of that stuff. I would try to come up with a way of phrasing the problem that you know, you don't need to see the result. Somehow the system can know the result. Somehow it observes it. Somehow I don't know how that is yet. But I would definitely try to avoid. Just to get the mechanisms right, I would try to avoid any of those complexities, because as soon as we introduce these other things and the aware pathway and so on, it's like, then it's opening up a can of worms, and you don't know. It's just really hard to pin down the solution.
Yeah, I wouldn't say it requires the aware pathway, but it seems like it would require voting between modalities at least, and like basically vision modality telling you the state. But then,
well, why can't we just make up a state for the object that's obvious to the 2 columns?
Well, I mean, can we just change it to pressing a button, and then it's just.
Well, maybe. Although I want to have different behaviors that are sequences. I like the idea of the finger
Pressing a button in like a Morse code, so you can do like.
You could do that. That's a different task. But that's not really. It's not really.
But then that's
less sensory motor. That's just temporal.
I guess then you still also have audition maybe to hear the tones. No, I don't know.
I think we need to make this task abstract, real enough you can understand it, but abstract enough that we don't introduce these problems. I think it's really important that the finger moves, that the sensor patch moves in space. That we're not going to be solving the problem correctly. And I'll have to learn different high order sequences to solve the problem. So we're going to use the temporal memory to do that. I'm just arguing for my case. I'm going to try to avoid anything else. I'm going to try to solve in 2 columns, at least get the first understanding done in 2 columns. You can't solve the whole problem, but then you can branch off from that. I think it's hard enough just to say, okay, what does it mean to tell region 2 you want a word, and who knows what that sequence is, and how is that sequence broken down, and how is the R1 executed? These are all interesting questions. There's a lot to unpack just trying to do something really simple there without moving the hand or looking at the screen or anything like that. That's my argument.
For instead of vision, you could substitute it with a linear buffer holding a character where a movement is moving one space in the buffer.
Maybe.
So like that,
Maybe.
that might be like the least amount of vision recognition feature I can think of.
Again, it could be a totally artificial way of the columns knowing what's going on initially.
And don't our fingertips have cameras in them anyway? Like we have vision right on the touch sensor. Like we don't have to worry about that.
Our fingers have it.
Well, the question is, well, that's an interesting question, right? Imagine, so the buttons are not equal, right? The buttons have different features, and those features could be, we could assume that they're tactilely detected. So we have a bunch of different features at different locations on an object, and we're trying to we're trying to press a particular feature, and we have to find out where that feature is. So the J key is a feature on the keyboard. It's not just a key, it's a J key. I sense the J, assuming like I can tactily touch it and feel it. So take that as a simplifying assumption. Now, basically, I have an object with a bunch of different features located at different points on the object. And my goal is to find the particular feature I want right now and move my finger to it. And then I'm going to do it for another feature in sequence. I think it's also, you know, what's really interesting too, I'm just thinking about right now typing. It's like we start with our fingers on the home row and the home keys, but as you type, you don't bring them back there every time, right? If I type the word jump, I move it up to the U, and then I would move it straight down to the M, and then I move it straight over to the P if I was doing it with one finger. So it's not like I'm going back to the home square again. So the sequence in which I execute is not completely right. That would be another interesting thing to learn. It's like the type of word, you don't go from home to A, home to letter, home to letter, home to letter. You somehow have to learn how to, instead of the word is actually the sequence of moving in a 2-dimensional direction around the keyboard. That could be all done in one column.
Yeah, I think
One
we can definitely work around like finding the sensor, finding the key letters and distinguishing the different keys with like the camera finger sensor or something like that. The bigger thing, and again, we can for sure use an artificial solution for it, but the state of the system, the state that we're trying to influence, so like the word appearing on the screen is not visualized in the keyboard itself. So the keyboard doesn't tell you which letters you pressed so far and where you are in the sequence. But yeah,
well, it would tell you which letter you're pressing because it has a sensor on it to detect that. Bear in mind, I'm not talking about something practical here. Maybe you guys are all thinking like we're going to build something that does something. I'm not thinking that at all. I'm just trying to think of a toy problem to elucidate mechanisms. So I'm willing to say
you could rephrase the goal as ensure all the keys still exist. Like the keys for Numenta still exist.
What?
And press them all, and once you're happy that they're all still there, the goal is accomplished.
Why would I do that? Why wouldn't I want to have the sequence of them?
Oh yeah, the sequence.
It's just like I have anyway, I've already said it. I think you could have think of an abstract model where you have like 10 locations, each has a unique feature on them. We'll call those letters of the alphabet, but and when the sensor goes to that location, it detects the unique feature. So I don't need a visual confirmation. Did I get the right input or did I not get the right point? And now the goal to understand how to go through a sequence of these movements in space to accomplish a broader goal of a word or sequence, and how the system would learn to do that rapidly, or it could do it if it was a new word, it would have to do it one letter at a time. But if it's a practice word, you don't have to think about it. It just automatically plays out. I think this is a very fruitful task, but it's not practical at all. It's just, I'm thinking about mechanisms. I'm not thinking about anything useful.
No, I mean, the only thing I'm pointing out is that like that higher level goal state of having pressed that sequence of letter is not observable in the keyword, but we could for sure do something artificial, like
but
when
it
you
is.
press the
If
key,
I-
it changes the color of the key or something like that.
No,
and
it's
it's been
it
pressed.
is observable in the keyboard. I'm saying each key has its unique feature. So the sensor detects whether it got to that feature or not.
Oh yeah,
It
it
says
knows
I-
when it's there, but it doesn't know if it has already pressed that key before.
Well, what do you mean?
Like, I don't, if I have already pressed NUM, and
Yeah.
how do I know that I've already pressed these keys? The state of the keyboard doesn't change as I press a
No,
key.
but the state of the
changes the
temporal
state of
memory
this.
of my motor behavior sequence is a temporal memory, and I know the state of it, and so I know what the next element I need to do.
Yeah. So the agent, the modeling system knows what you've done so far, but there's no way to compare whether you actually achieved your goal state.
I guess in the higher level, like the learning modules that can detect these, that both knows the concept of like this series of unique sensations, and which is also the one that's kind of guiding the overall task. Like that one's going to get. I mean, we could say like it only feels it when it presses it. Like I don't know, it's almost like a depression that comes out or something. But like
It
it's
doesn't
going to
have
feel
to
that,
press
and just like any kind of Monty system or whatever, over a series of movements, it'll be like, okay, I detected that feature, I detected that feature. So it will
knows-
kind of satisfy what it's requesting.
It'll know if it's successful, because if it's been learned as a sequence, it knows what the next element should be, and if it isn't the correct next element, it'll know it's wrong. So if you do if it's learned numenta and it's a rote sequence, and you do NUM and it doesn't detect E next, it knows it's got a mistake. So I think it's built into the system that it'll know whether it succeeded or not. I don't see a problem with that.
I think
I'm overloaded. I'm putting it all on this one little sensor. Just imagine there's 10 unique features on an object arranged in some physical arrangement, and the sensor knows whether it gets to that point or not. It doesn't even have to press it. It just has to get to that location, and that would be like, it's like a keypad. It's like just if it followed if it got to the right sequence of elements, it succeeds.
in terms of the task, I'm just wondering, like, it feels like we would rather have something where it's not like a learn sequence, but more like, okay, you now need to type this series of letters. Can it plan that out? Because otherwise, yeah.
It starts off unlearned, right? It starts off that, like a new typist, you have to use your model. First, learn the model of the keyboard, where the different features are. Then say, given my current location, how do I have to move to activate a particular feature, get to a particular feature?
So that can't use temporal memory because you've never done that path before.
Right. That's it. You're using the model. It's path integration or reverse path integration.
Okay. I guess I was just concerned that we were talking so much about doing something we'd done before that I felt like we'd go down a path of only using temporal memory.
No. It starts out obviously nothing learned, and first you have to learn a model of the object. That's pretty simple in this case. It's a set of features in some physical arrangement. Then then the goal is to, given a particular goal, you have to navigate through one at a time through those different through a set of those elements, just moving your finger to those elements in the right order. That is going to be that's not wrote yet, but if you do it enough times, it will learn to do that automatically. So that would be one of the goals of this system. Is you start off slow and methodical, which is even hard enough to imagine how to do that. But then once you've done it enough times, it gets really fast. As long as you locate the finger in the right position, it just follows the sequence automatically. And again, then we could show it a new word it doesn't know, and it would have to think about each letter again. You know, if I gave you some random sequence of letters, it didn't look like any word you knew, you'd have to think one letter at a time. Now, how do I do this letter, then this letter, then this letter, then this letter, decompose it? I think all this could be done in 2 columns. At least
Yeah, I think
at the moment.
if you're formulating the problem like that, it could be, but maybe it just feels a little bit sad to do it that way because we're losing like actually manipulating the state of the world. Like we're not actually changing the state of the keyboard at all, and we're not learning this behavior
Well,
of like, when I
okay,
press
but
this button, the state actually changes.
I don't think it's sad. I think you just have to realize you're doing it in a simple way that may not look like the way you typically think about it. Perhaps the state, we haven't defined what the state of the object is yet. We don't really know that yet. We're talking about it. We don't really. So maybe the state of the object is literally, have you gotten it into the position at this location in the sequence? And meaning you've done the particular right order, and that is the state. It's now in the word numenta. I could think now maybe that's not a physical state, but I could modify this 2-point problem to say I could even modify the problem to say as you touch the keys, they move around. And so depending on where you are in the sequence, you have to go to a different location, right? So I think that again, I personally have to think about this in the most simplistic form. I'm trying to fit as much as possible in 2 columns. You might think it's sad, but I don't think it's sad. I think it's the way of making progress. So I'm going to try to do as much as possible at that. And then, of course, most people won't understand why that's important. But once you got the mechanisms, then we should be able to expand it rapidly to do real world things. That's my argument.
Yeah, I also wonder whether it would be helpful, because I think for me, the complexity that still feels like it's very there, at least in the like real world imagining of this, is like the coordination of the hand and the finger that's attached to it. Like that's definitely gonna be, non-trivial if it was actually like a robotic arm or whatever. But I don't know if we say it's like some almost like a digital space where you just have like, the 4 arrows on a game pad or something, where you go up, down, left, right with like a cursor. And so you kind of have to visit locations or something. Yeah, I guess to me then it's easier to understand how one column can kind of coordinate that.
About how we're solving robotics, they're not going to get excited about this. But it doesn't matter. These are really hard problems. We have to get to the core of the mechanisms. And I think we will run into dead end.
Yeah, it wasn't a criticism that it's too simple. It's too simple. It was more just like, it was more almost like it wasn't simple enough. Like I'm just worried that if we're talking about a finger moving, like inevitably it's going to come back to like, okay, well, how does the hand get the finger into the right location and stuff like that? So I'm just wondering if it's useful to have a motor actuator that's even simpler than that.
Well, I think all I'm saying is that the hand doesn't exist here. The finger there's sort of like a finger that's anchored in object space, and then the movement is how to move the tip of the finger to the right location to solve a particular problem. It's a navigation problem. It's not obvious to say, oh, once I have a model of the object, how do I get from this letter to that letter? We know that grid cells can do that. No one really knows how. There's some speculation about it. So we have to solve that hard problem. We have to solve the decomposition of sequences into or goals into subtasks. We have to know whether we completed the subtask or not. There's a lot of hard stuff to solve in this really simple problem. So I just can't imagine tackling more at once. It just seems like until I get the core of this stuff down, everything else, it'll just be like, I think we'll waste time. We'll think about these high level goals and we'll just, it sounds good, but then you try to build something, you just won't know how to do it. That's been my experience.
I think it can be done by 2.
We don't have to agree, by the way. We can take different approaches to this. I'm sorry, what are you saying?
Yeah, no. I'm also okay. Yeah, I'm also trying to suggest keeping
I'm
it
beginning
simple.
to think that it can be done by 2 columns. So let's say like I have 1 finger, no eyes, and first I need to learn, right? So I'm gonna just like go through the keyboard. Sorry.
Learn a model of the keyboard.
Learn a model of the keyboard. I can, there's a feature, there's some protrusion, let's say, so I can tell that to N, I can tell that to U, whatever.
Right.
So I learned it, and then let's say, there's a goal of typing Numenta. So actually when we're learning, so we're learning the keyboard, not like feature allocation, right? So there's N at 0, something, U at 0, 1, so whatever like that. And then, and let's start from the easy case, not just putting the hand, on it or like finger on it, but let's say we are at N and we want to type Numenta. So we break down the goal so that so now we want to type U, and so the goal is go to U, and it will have to use some features learned at level 1, like N at 0, and U at, I don't know, 2, and R2 will need to figure out like integrate that information. Okay, then like move right to up to. And then
I think R2, let's say R1 learns the model of the keyboard.
Yeah.
R2 has to know, my first blush would say R2 is telling R1 there's different states it needs to get into. First you have to get to the end state, then you get to the U state, M state, and R2 has to know that R1 has accomplished that somehow.
Yeah.
And then it gives the next one and the next one and the next one. What will happen as the system gets practice and practice and practice, that R2 doesn't have to tell R1 to do all those steps.
Yeah.
R2 will say, hey, in the context of this word, before I was telling you how to get to all these different points. So maybe there's two things being passed down. One is like, we're doing the word Numenta now, but you have to do the N, then you have to do the U, then you have to do the M. But after it gets practiced, R2 says R1 do the Numenta, and R1 just does it. It just goes bing, 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 and goal accomplished.
Yeah.
That's how I'm viewing it. So
Yeah.
R1 has the model of the keyboard. I don't think R2 even has to have a model of the keyboard.
Right.
It just has to have a model of the word Numenta.
Yeah, I mean, and I think goals can also be broken down like infinitely, like, in the beginning, there might be a lot of step goals like that we need to think through, but when we're used to it, there's not as many goals. If we don't have infinite number of layers, so at some point, like R1 will need to figure out.
But also just bear in mind that in the hierarchy, just like in composition, all the hierarchical steps are not represented at the same time.
Right.
You can just do it with two levels. You can move those two levels up and down in the stack of hierarchy. So I'm solving this problem now, I'm jumping down, solving this problem, I'm dropping down, solving that.
Yeah.
It's like a task may have 20 different sort of complex, I don't know what it would be, but they're not all represented at once.
Yeah.
Anyway, that seems like an requirement. Yeah.
What else were we supposed to talk about today?
Well, this was the topic, I guess.
Okay.
Yeah, this was the top. This was the aim.
Okay.
Unless Vivian wants to talk about something, she was offering to review some anatomy, but
Oh, I can do it next time. I think we're already over time, so.
okay.
Oh, okay.
Well, I'm really excited about working on this now. For me today, this meeting was really helpful for me. I don't know about anyone else, but really helpful for me. Just talking through this made it much more clear what my task is or what our task should be. And so I'm excited about that.